carry on with section 11.2, the silicon controlled rectifier, or the SCR. You can also mark the introductory paragraph there again. Like the 4-layer diode, the SCR has two possible states of operation. On or off. In the off state, it acts ideally as an open circuit between the anode and cathode. Actually, rather than open, there's a very high resistance, as we've learned earlier with the diode as well. In the on state, the SCR acts ideally as a short. From anode to cathode, actually, there's a small on or forward resistance, basically the same as we've discussed with the diode as well in electronics 1. The LA SCR operates as an SCR, except that it is triggered by light, but I will show it to you when we get there. Alright, firstly, the SCR. You can see the similarity to the device that we've discussed previously, the 4-layer diode. Again, 4 layers, like in the 4-layer diode or the Shockley. Again, the anode and the cathode, but in this case, there is a third terminal added called the gate. We will discuss this just now. Of course, you also have to know the schematic symbol. You'll see it's similar to a normal rectifier diode, only that there's a gate terminal added to the schematic as well. And here at the bottom, I can see there's some typical packages of what an SCR would look like physically when you go and buy it. Alright, on page 558, and have a look at the SCR equivalent circuit. Because of the 4 layers, I can see here I have an equivalent circuit as indicated here, with the top 3 layers will form a PNP transistor, and then with the bottom 3 layers as indicated here, I have an NPN transistor. So for the equivalent circuit then, the will be formed with Q1's collector connected to Q2's base, and that will form the gate terminal. So you have to know how to draw the transistor equivalent circuit of the SCR as well. Alright, let's have a look at the operation of this device. Figure 11.9, the SCR turn-on process with the switch equivalents as shown. When the gate current IG is equal to 0, as I can see here, as shown in figure 11.9a, the device acts as a 4-layer diode in the off state. In this state, the very high resistance between the anode and cathode can be approximated by an open switch as indicated right next to it there. When the positive pulse of current, a trigger is applied to the gate, as I can see here in the B part. Both transistors turn on. The anode must be more positive than the cathode, of course. This action is shown in figure 11.9b. IB2 turns on Q2, providing a path for IB1. You can see here, there's IB2, and when that transistor switches on, it forms a path for IB1 into the Q2 collector, thus turning on Q1. The collector current of Q1 provides additional base current for Q2, so that Q2 stays in conduction after the trigger pulse is removed from the gate. By this regenerative action, Q2 sustains the saturated current conduction of Q1 by providing a path for IB1. In turn, Q1 sustains the saturated conduction of Q2 by providing IB2. Thus, the device stays on until it is triggered on. Once it is triggered on, as shown in figure 11.c. In this state, the very low resistance between the anode and cathode can be approximated by a closed switch, as indicated here in the last part. But let's have a look at the characteristic curve so that we can see the similarity of the 4-layer diode. This device can also be used as a 4-layer diode, but it wasn't designed to be used that way. As we can see over here in figure 11.10a. You can see it's very similar to the 4-layer diode where I increase the forward voltage. And up to a certain point, which is called the forward breakover voltage, the device switches on. You can see here, then there's no gate voltage. No? And this device remains on as long as forward current or the anode current remains larger than the holding current. Alright, so it can operate the same, but it's not designed that way. It's got a third terminal called the gate. And if I go and look here at figure 11.10b, where I have various IG values, that's gate currents that's been applied, the gate voltages. So if I gave pulses to this device here at these various positions on the forward voltage, I can decide when I want to switch this device on. Eh? So if a pulse is given there, I can see there the device switches on, and it will remain on as long as the anode current again remains larger than the holding currents. Alright, so if you are asked to draw the characteristic curve for an SCR, please draw this one where you indicate the various gate pulses with the various forward breakover voltages and the various holding currents for these different pulses that has been applied to this device. Alright, so that is the SCR's characteristic curve. Remember to include all the labeling to be able to get your marks. Alright, then we also have to know how to turn this device off. I'm going to have a look at a few methods to do that. Figure 11.11 on page 560. We start with the first method there, which is called anode current interruption. Please, ladies and gentlemen, remember it's anode current interruption, not just anode interruption. There's no such thing as anode interruption. Alright, the first method here, there are two methods under anode current interruption. The first one is I can put a switch in line with the anode current. And of course, if I open that switch, of course, the anode current will become 0, which will be lower than the holding current of the device, and the device will switch off. The other method is to put a switch in parallel with the device, the SCR device, a push button switch. So if I push that switch momentarily, I can see that the anode current will be relayed via the switch to ground, bypassing the SCR, and of course the anode current again becomes lower than the holding current, and the device switches off. You have to be able to name and draw both these methods for anode current interruption. Alright, the second method, figure 11.12, is called forced commutation. Please note the spelling. It is not called forced communication, as so many students in the past told me in the test. Forced communication is what I'm doing to you right now. I'm talking and I'm forcing you to listen. That's forced communication. This, however, is forced commutation. Alright, how does it work? You can see here I've got some circuitry included here in parallel to my SCR device, the switch again with the SCR device. And what happens is my capacitor charges from the voltage, supply voltage, whatever the voltage may be. And when I do close the switch, you can see from the capacitor charge, I will have a current flowing in this direction, which is in the opposite direction than the anode current. And I know if two currents are flowing opposite to each other, they will subtract. The anode current will become smaller than the holding current, and the device switches off. That is called forced commutation. That's the second method of how to switch an SCR off. Alright, at the bottom of page 560, just below figure 11 and 1112, there is some SCR characteristics and ratings of which you will find, of course, on the data sheet of which you have been introduced to in Electronics 1 concerning a normal diode. Of course, we do get data sheets for all electronic devices. So if you do need to use an SCR or design a circuit using an SCR, of course you will go to a data sheet to determine what kind of SCR you will use. Of course you will get information there, like is mentioned here on page 560, the forward breakover voltage, holding currents, gate trigger current, average forward current, and so forth. Okay, so familiarize yourself with those terms, of which you will find also on the data sheet. On page 561, also mention is made of the light activated SCR, or the LA-SCR, of which we've seen in the introductory paragraph that it works exactly the same as a normal SCR, only that this one is light activated. You have to know the symbol, of course. You can see this symbol, however, is encircled. You don't have to include the circle. Which is important, of course, is the arrows pointing towards the device showing that it is light activated. All right. Figure 1114, there you can see there's an LA-SCR circuit used to energize a latching relay. The input source turns on the lamp. The resulting incident light triggers the LA-SCR. The anode current energizes the relay and closes the contact. Notice that the input source is electrically isolated from the rest of the circuit. You can see there's no electric connection in there between these two, because it is a light activated device. One of the advantages of using this type of device. We will have a look at some of these devices later in the semester as well. Alright, this concludes then section 11.2 on the SCR.